Today I will give you the presentation on my master's thesis with the title Localization Structures for Free Quantum Fields. And it will be mostly about classification of maximal localization structures. So first I will give you a brief introduction into representations and free quantum field theory. Then I will define and also give some basic properties of maximal localization structures. And finally the main result, which is the classification for spin zero. Okay, the hope that we had before we did this project is that we can understand the locality in relativistic quantum theory and in the Hilbert space picture rather than in the algebraic quantum field theory framework. And the main leading question is, how do locality and causality prescribe the spin statistics connection? Okay, the goal, to formulate it more mathematically, is we have an irreducible unitary representation of the Poincare group with spin S, and what follows then is there exists a maximal localization structure which is unique up to a global phase. And if the spin and statistics connection doesn't match, then the maximal localization structure is the trivial one. So basically we have no local Hilbert spaces or local state spaces, and otherwise we have the one that is induced by the Fourier transform. So what are the representations of the Poincare group? The spacetime interval is the basic structure of the Minkowski spacetime. Time-like vectors or time-like points can have causal relations, whereas space-like points cannot, and light-like points can only have signals traveling at light speed between each other. The Poincare group then consists of all the transformations that leave invariant the causal structure. And here, for example, I have plotted lines behave under Lorentz boosts. So free quantum fields now consist of irreducible unitary representations of the Poincare group. We know that the space-time translations can be represented as some multiplication operator that looks like a Fourier transform. So to be irreducible, we now look at the Lorentz group, which are the non-translations of the Poincare group, and there the orbits are, so to speak, irreducible. So all in all, we have square integrable functions on the mass hyperboloid, for example, with values in the spin S representation space of the rotation group, which is the stabilizer of points on the mass hyperboloid. So the special unitary groups in two complex dimensions. Then we look at the induction of representation. So we have the representations on all of the fibers, on all of the complex vector spaces at each point, and also a representation on the orbit. So we have a combined action on the orbit and also on the fibers. So for those Hilbert spaces with this action of the Poincare group, we now define maximal localization structures. A first condition is causality. So in quantum field theory, we're looking at multiparticle states, and for fermions, this is the anti-symmetrized Fock space, and for bosons, the symmetrized Fock state space. And because we want the field operators to satisfy the canonical anti-commutation or commutation relations, this then encodes the causality, because if we have space-like separated field operators, we want them to commute or anti-commute, and therefore the respective part of the scalar product needs to vanish. For this space-like separation, we can also look at the causal complement of a set in Minkowski spacetime, and it's defined as all the space-like points that are space-like to the respective set O. And we have some examples. So for a point, it's the outside of the light cone, and for a wedge, it's the other wedge, and so on. And as I said before, the real and the imaginary, or the imaginary part of the scalar product has to vanish for things that are separated or in the causal complement. The localization structure now defines for space subsets of the space-time so-called local state spaces, and that is for all of the regions we have a subset of the Hilbert space that is local to that region. And we need three conditions, namely first isotony. So if we have a smaller region of spacetime, then the states that are local in that region are also local in a larger region. Then we need covariance. So if we transform our region with Poincare transformation, then we want this to be equivalent to the unitary action on the local state space. And finally, the causality condition that I explained before. So if two sets are causally separated or space-like separated, then depending if we have a bosonic or fermionic localization structure, then the real or imaginary part of the scalar product between states that are localized in the different regions vanishes. So now we have some basic properties of localization structure. First, there is the so-called standard localization structure, which is basically a Fourier transform from the position space to momentum space, and we just move the locality by this Fourier transform, and also there are generalizations to higher spin. Then there's the trivial localization structure, where we have no local states to any of the sets. One can also check that both of them really define a localization structure. Then a property that can hold for some, but may not hold for any localization structure, is duality. So if we have the causal complement of our spacetime region, then the states that are local to the causal complement are the symplectic or the real orthogonal complement of the space states that are in our original spacetime region O. And one can also restrict to collection of subsets or collections of spacetime regions that are closed under causal complement, and also extend to other collections of subsets if we have some regularity conditions. For us, it will be important to look at double cones and wedges because they are important collections of subsets. The wedges are basically cut through the spacetime in a wedge-like shape, and wedges and double cones are the intersection of one forward light cone and a backward light cone, so that we have a double cone. As we've seen, the localization structures are not unique, and we can have lots of different localization structures, but what we assume, or what we want to show, is that maximal localization structures are unique, and therefore we need to define an order relation. So we have two localization structures on the same collection of spacetime regions, and then we say localization structure S1 is smaller than S2 if the state spaces are included. This necessary condition for maximality that we proved also implies that the local state space is a real vector space. We now have a sort of geometric reduction argument. It's the so-called separation by wedges theorem. So the separation by wedges means that for all compact convex regions of spacetime, we find wedges that separate them. Using covariance, we can then go to a single wedge because all the wedges are related by Poincare transformations. We now have the classification for spin 0 that we also would like to extend to higher spin. We now also work in the complexification of the Hilbert space because we want to relate the symplectic complement to a complement in the complexified Hilbert space. Then we use the symmetries of the wedge, that is rotations in the transversal directions, translations in the transversal directions, and boosts in the wedge direction. With that we define a Fourier transform, and the symmetries then allows us to deduce that we have a point-dependent projection in the Fourier transform picture. And that reduces the dimension of our problem because we now relate this projection to the projection of a 1+1 dimensional wedge subspace. Using then another property, that is, if we translate the wedge into itself, that it basically is isotenous, then we get the uniqueness of the 1+1 dimensional wedge projection up to a global phase. That, however, doesn't fully fix the phase of the 3+1 dimensional localization structure. Therefore, we have different choices of phases along the transversal directions, which only depend on the radial coordinate of the 2 and 3 direction. And to finally prove that this phase is constant, we use that we want the intersections of the wedge subspaces for small rotations or for arbitrary rotations are maximal. Therefore, we use the standard localization structure, and that is basically a Fourier transform to give us uniqueness of this phase, or that this phase is constant along the whole transversal direction. This argument now showed that the spin 0 and mass m representation have a unique maximal localization structure, which is the one defined by the Fourier transform, and we also know that it is a bosonic localization structure and that the fermionic causality condition can only hold for the trivial localization structure. So to conclude now, we have uniqueness and the spin statistics connection for spin 0, and we think that the result for higher spin seems also possible but requires some extra effort. And it was a lot of fun to experiment with the structures and to find some small examples to play with. And what was most interesting is the complexification, that it basically relates real orthogonal complements or real scalar products to Hermitian scalar products. And also a thing that we wondered about was what does this PCT theorem mean and how does it relate to our investigation. Thanks for your attention and see you around next time.